we can have a discussion about acidity of phenols. Phenols are acidic. While performing the qualitative analysis of organic compounds in our lab, we have classified or grouped these phenols under group 3 based on its solubility in 5% sodium hydroxide. So what were the other compounds that belong to group 3? Salicylic acid, cinnamic acid, phenol, etc. That means phenols are acidic. They are soluble in sodium hydroxide. So phenols are converted into their salts by aqueous hydroxide. So in this equation we can see that the phenol AROH, when it is allowed to react with any hydroxide ion, phenol, it donates one proton to hydroxide ion and phenol is converted to phenoxide ion ARO minus, and we got a weaker acid H2O from a stronger base hydroxide ion. So the stronger acid AROH, it donates a proton to a stronger base OH minus, and this AROH is converted to phenoxide ion ARO minus. And the salts can be converted back to phenols by treatment with the mineral acids. So in the second equation, the ARO minus, the phenoxide ion on treatment with a mineral acid like carbonic acid H2CO3. From the mineral acid, it accepts a proton. It is a stronger acid. Mineral acid H2CO3, it is a stronger acid. So it donates a proton to this phenoxide ion, or we can say that phenoxide ion accepts a proton from the stronger acid and the phenoxide ion is converted to phenol. So phenols are stronger acids than water but weaker acids than carboxylic acids. We know that the acidity constant Ka value gives us an idea about the measure of the acidity of an organic compound. So phenols, they have a Ka values of 10 raised to minus 10, and for carboxylic acid the Ka value is 10 raised to minus 5. And alcohols are also acidic and they have a Ka values of about 10 raised to minus 16 to 10 raised to minus 18. So if we arrange these carboxylic acids, phenols and alcohols in the order of the acidity, carboxylic acids have more acidity, then comes phenols, and alcohols have the least acidity. Now we have to see why it is so, why these phenols are more acidic than alcohols. So for that purpose we have to estimate, we must have an idea about the difference in stability between the reactants and the products. So you know that alcohol and alkoxide ion can be represented by a single structure. So alcohol can be represented as ROH. When it donates a proton, alcohol is converted to RO minus. It is the alkoxide ion. So alkoxide ion also can be represented by a single structure. So when we compare, when we state about the acidity of the alcohol, we cannot say that the alcohol is more stable than alkoxide ion or the alkoxide ion is more stable than alcohol, because both the alcohol and alkoxide ion can be represented by only one structure. In order to prove that phenol is more acidic than alcohol, we have to compare the stability of phenol and phenoxide ion. So we know that phenol has a benzene ring. So whichever compound that has a benzene ring can be represented as a hybrid of two different kecular structures. So phenol has two structures, two kecular structures. So phenol actually it is a hybrid of these two structures, structure 1 and 2. So when the phenol donates a proton due to its acidic property to any other base, phenol is converted to phenoxide ion. Phenoxide ion also has a benzene ring, so it can also be represented as a hybrid of two different structures, that is structure 3 and 4. So if no other factor is involved, we cannot say that the phenoxide ion is more stable than phenol, because by considering only kecular structures, resonance stabilizes phenol and phenoxide ion to the same extent. So we cannot say that phenol is more acidic than alcohol. But besides this Kekulé structures for phenols and phenoxide ion, two structures each, we have to consider some additional structures. We know that oxygen is basic and it has the tendency to share more than one pair of electron with the benzene ring. That means it can exert its resonance effect. When the oxygen shares one more pair of electron with the benzene ring, the negative charge will be distributed or localized at the ortho positions and para positions. So as a result, we can draw additional 3 more structures, and moreover in that particular structures there is a positive charge on the oxygen and negative charge at the ortho positions and the para position of benzene ring. So the structure of phenol, it is a hybrid of 5 different structures. But when we consider phenoxide ion also has a negative charge on oxygen, and the oxygen is ready to share more than a pair of electrons with the benzene ring. This also results in the formation of double bond between oxygen and benzene ring, and moreover the benzene ring receives a negative charge. But the thing is that here the oxygen is not having a positive charge. Why? Because oxygen initially it was having a negative charge. So when it donated or when it shares one more pair of electron with the benzene ring, that negative charge is getting neutralized. So there is no positive charge on oxygen. So total 5 structures are possible for phenol and total 5 structures are possible for phenoxide ion. So but when we consider the number of structures it is same for both phenol and phenoxide ion. But when we analyze the structure for phenol, the 3 structures have positive charge and negative charge on the same structure. So if in a particular structure both positive and negative charge is there, the energy content of that particular structure will be high. So as a result, that particular 3 structures will be less stable. But in case of phenoxide ion, all the structures out of 5 structures, not even a single structure is there having a charge on oxygen atom. So the structure of phenoxide ion, which is a hybrid of 5 different structures, it will be more stable than structure of phenol, because in phenol out of 5 structures, 3 structures are having both positive and negative charge. So whenever there is a structure having positive and negative charge, such structures will be having more energy and they may be less stable. So we can say that phenol is less stable compared to phenoxide ion. That means phenol will be having more tendency to exist as phenoxide ion. So in order to exist as phenoxide ion, phenol should donate a proton to any other bases. That property of donating proton is called the acidic property. So phenols are more acidic. Phenols have more tendency to donate the proton and to exist as phenoxide ion because phenoxide ion is more stable. Little more explanation about acidity of phenol. So acidity of phenol is due to its ability to lose hydrogen to form the phenoxide ion that we know. And in phenol molecule, the carbon atom to which the hydroxyl group is attached, it is the carbon atom of a benzene ring. And we know that the carbon atoms of benzene rings are all sp2 hybridized. So the electrons present in the sp2 hybridized orbitals, they are situated more close to the nucleus. So they can act as an electron withdrawing group because they are strongly pulled by the nucleus. So as a result, the sp2 hybridized carbon atom of the benzene ring, it has higher electronegativity, and this leads to decrease in electron density on the oxygen atom, because the electrons present on the oxygen atom of the hydroxyl group, that is pulled more towards the carbon atom because the carbon atom is sp2 hybridized. So the decrease in electron density increases the polarity of the OH bond. That means From the OH bond, the hydrogen can easily come out as H plus by leaving behind the electrons. There is an electron pair between, there is a bond between oxygen and hydrogen. The hydrogen can leave as H plus by leaving behind its electron pair. And because that particular oxygen atom of the hydroxyl group, it is having less electron density. Why it is having less electron density? Because the electrons present on the oxygen that are pulled towards the carbon atom, because that carbon atom is sp2 hybridized orbital. So sp2 hybridized. So what happens? The electron density on the oxygen being less, that particular oxygen can well accommodate the electrons left behind by this hydrogen, and so that this facilitates the ionization of the phenols, because phenol is converted to phenoxide ion by donating a proton as, or a hydrogen as H plus or as proton. So thus the phenoxide ion is formed, and the phenoxide ion is stabilized by delocalization, as we have seen in the previous slide. The negative charge is delocalized over the para positions as well as the ortho positions. So we can conclude that phenoxide ion has greater stability than phenol, and in phenol there is a charge separation. Phenoxide ion there is no charge separation.
Yeah.
What is the effect of substituents on acidity of phenol? Phenoxide ion has a negative charge. Any substituent that can disperse the negative charge will increase the stability of the phenoxide ion and increases the acidity of phenol. So we know that electron withdrawing groups, they can disperse the negative charge of phenoxide ion, increases the stability of the phenoxide ion and increases the acidity of phenol. And electron releasing groups, that will intensify the negative charge of phenoxide ion, decreases the stability of phenoxide ion and increases the acidity of phenol. There is another explanation why these electron withdrawing groups like nitro group, Cl, cyanide group, CHO, COH, etc., they increases the acidity. The explanation is that the nitro groups, it helps the ring to withdraw more electrons from the phenoxy oxygen, so that the phenoxy oxygen, it becomes more polar, or it can well accommodate the electrons left behind by this hydrogen. That is another explanation for the effect of electron withdrawing groups, how it increases the acidity of phenols. Here are some reactions of phenols. When we treat phenols with aqueous solution of bromine, that results in the replacement of all the hydrogen atoms at the ortho and para position of this OH group, and sometimes it may even cause displacement of certain other groups. Here we can see in the first reaction there is the orthocresol. Orthocresol, when it is allowed to react with aqueous bromine solution, we can see that the hydrogen atoms at the ortho position and the para position, that is replaced with and substituted with the bromine, and you got 4,6 dibromo 2-methyl phenol. 2-methyl phenols are commonly called as orthocresol. And in the second reaction, the paraphenol sulfonic acid, when it is allowed to react with the aqueous bromine, we can see the hydrogen atoms at the ortho positions as well as the sulfonic acid group at the para position, that is also replaced and substituted with the bromine atoms, resulting in the formation of 2,4,6 tribromophenol. So phenols can be converted to picric acid that we have synthesized in our lab. So when phenol is treated with nitric acid, we may get 2,4,6 trinitrophenol. And if we want to prepare mononitrophenols, we have to just dilute this nitric acid, and the temperature also should be kept at a minimum. Here phenol, when it is treated with dilute nitric acid, you may get a mixture of orthonitrophenol and paranitrophenol.